This is the last class of this week. In the last week, we discussed the equations. We did not derive this equation. The reason is the derivation of those equations are very similar to the derivation in Cartesian coordinate system. We just saw the final expression for the governing equations in polar coordinate system, and then also we have seen what is the final expression. If we use the stress function approach, then what is the final expression in terms of stress functions when the body force is 0. And then we also saw what is the general solution of that expression. We did not explicitly solve that equation, we did not derive that solution, but the reference where the solution is given in detail, that was also mentioned. It was also mentioned that the one point that we that a statement that we made some time back, that compatibility condition helps us to arrive at unique displacement field, but it may not be so. It may not be guaranteed always, especially when your problem becomes your domain becomes non-simply connected or multiply connected domain. And this has, you may find out, you may this has a very very serious application, and that application we discuss when we talk about complex variable approach. Especially suppose you have a problem where you have some cracks or defects. In those cases your problems not from the geometry, but because of the presence of defects and presence of small crack or crack like flaws, your domain becomes multiply connected, or in the process it becomes multiply connected. In that case the uniqueness gets violated. We will discuss that in details later. And then what we will do today is we will take up one or two example in polar coordinate system, and then see how the problems in polar coordinate system can be solved, how the stress field can be determined, how the displacement can be obtained using Airy's stress function method. We will just take one or two examples, but if you take any book, there are many examples given, many exercises given. So, please, this is just for your reference and for understanding the steps, but you have to follow all the examples, many examples given in the book. Okay. With this statement, let us start. Recall, this is the final expression, the biharmonic expression in the absence of body force. The solution of these expressions given in these two. These are the references, and the general solution of this expression is this that we discussed. Okay. We also discussed for an axisymmetric problem, we can make all these theta dependent term in the stress function, means all these term like all these term where we have theta explicitly, we can remove them and take only this term as our stress function. Okay. And then we also have seen that if we take this term as our stress function, then this is the definition of Airy's stress function, and then if we substitute that definition, we have expression for sigma r and sigma theta as this. Okay. We have also seen that if your domain is a simply connected domain, then this stress function can only give you a constant stress field. You cannot get more than that if you take this as your stress function. Okay. Now, the problem, so this is we know. Okay. Now, let us take one example. It is a non-simply connected, it is a multiply connected domain. So, therefore, that restriction we had, that restriction means only constant field can be represented through that stress function for a simply connected domain. That restriction we do not have here. So, this is the problem. Let us complete the description of the problem. So, domain is given, the forces and everything is given. So, the boundary conditions, which is one of the very important part of problem description, and the boundary condition, if you look at this, the boundary conditions are that sigma r is equal to, if you write the boundary condition here, sigma r is equal to, say at r is equal to r1, is equal to minus P1 and sigma RR at R is equal to R2 is equal to minus P2, right. This is the boundary conditions. Okay. We can also have the boundary condition, for instance, the sigma theta theta on sigma r theta on the surfaces are 0. Okay. So, this is the boundary. Now, what we do is we have, let us take our stress function. If you go back to the previous slide, this is our stress function. Now, and corresponding sigma r is this. Now, suppose this logger term, if we do not take the logger term, okay, means if we make A3 is equal to 0. Now, we have to start with some assumption of stress function. Let us make a simple assumption, make A3 is equal to 0. So, this term will go. So, essentially we are left with this term and this term, this term and this term. Okay. So, which can be written as, now I leave it to you, please see why I have ignored the logger, this A3 term, logger term. If I take logger term, do this exercise please. If I take logger term, the steps that we will be following now, follow the same steps with A3 non-zero and then see what happens. Now, so this is the problem description, right. Now, okay. So, the boundary condition is given. So, if I remove the logger term, what we have is sigma r is equal to, say sigma RR is equal to, say A by R square plus B, which A was actually A1 and B was 2A2, and corresponding sigma theta theta is minus A by R square plus B. This is expression for sigma RR and sigma theta theta. And what is the boundary conditions that we have? The boundary condition we have is this, that sigma RR at R is equal to R1 minus P1 and sigma RR at R is equal to R2 is equal to minus P2. That is the boundary condition we have. Please minus P, because this is compression. Had it been like this, it would have been plus 2 plus P. Now, if we substitute this into this expression, we have two constants here A and B, we have two equations, and if you substitute that, then we will get the expression for A and B as this. Please do this exercise. I am writing the final expression only, R1 square R2 square into P2 minus P1 by, please check that expression also, do not take it for granted, R1 square, and then similarly we have B is equal to R1 square P1 minus R2 square P2 by R2 square minus R1 square. So, this is the expression of A and B we have by, if we apply these boundary condition. Now, next is, now here one important point, consider it is a plane. Let me first give you a physical implication of this problem. This problem is essentially, suppose you have a cylinder like this, you have a cylindrical vessel like this, and on this cylindrical vessel we have some internal pressure throughout the length, and also suppose we have some external pressure from outside. Okay. This is also over the entire surface, Okay. Now, this is a plane strain problem. This dimension is very large. So, we can do the analysis by taking just only one plane, and if you take a plane, just take a plane, this plane is something like this, and this is this problem. Okay. We have internal pressure and then external pressure. Then we will see what happens when we do not have. This is a very general case. You might have done cylindrical pressure vessel in your in solid mechanics or strength of material, where we have only the internal pressure, no external pressure. In that case, you can make P2 is equal to 0, but it is a very general case. Okay. So, this is a plane strain problem. Now, plane strain problem means then we can have stress in z direction. The sigma zz, there will be some sigma zz along z direction, and that sigma zz can be obtained by sigma rn and sigma theta theta. If you recall, in that case sigma zz will be sigma zz will be nu into sigma RR plus sigma theta theta. That is how for plane strain problem the other component of stress can be obtained. Okay. So, next is we substitute A and B into this equation, get expression for sigma RN and sigma theta theta, and then substitute sigma RN and sigma theta theta here, we get an expression for sigma Z. Okay. Now, if we do that, what we have, final expression of sigma RR, these are all sigma RR, please correct it, sigma RR, sigma theta theta, and then sigma ZZ will be equal to this, sigma R theta will be 0, sigma R theta will be 0. Okay. This is the expression for different stress components. Okay. Now, so once we have the stress components, now recall for plane strain problem. So, these are the stress components we have. Now, we can substitute these stress components here and get an expression for epsilon RR, epsilon this substitute sigma theta sigma R in this expression and get expression for sigma RR, sigma and sigma R theta. Okay. All the epsilon RR, epsilon theta theta we can obtain. Once we have the strain component, then we know the strain displacement relation. These are the strain displacement relation. So, we know sigma RR now from the previous slide, sigma RR known, sigma theta theta known, then you have to integrate it, sigma RR, say epsilon RR, epsilon theta theta and epsilon R theta. If you integrate it, then we get displacement. In that integration, we will have some constant, that constant need to be determined based on the boundary conditions. What are the displacement boundary conditions given for this problem? Okay. Now, if you do that exercise, then the expression for UR will get this. This is the expression for UR. Please do this exercise. Now, so this is the complete solution of this problem, where is A and B are are the constants. Okay. Now, so before moving on, let us if you recall in the introduction to this course and also on various occasions, it was mentioned, you see, whenever you use any theory, every theory is based on certain assumptions, and assumptions are very important because assumptions are limitations for any theory. You recall, you have studied cylindrical pressure vessels in your strength of material course or in solid mechanics course, and you obtain some result for hoop stress, right. Now, this is also a pressure vessel, but in this case it is, we have not, when you obtained that the results for hoop stress, you made some assumption like say thickness is very small, therefore, it can be considered as thin wall pressure vessel, whether it is thick wall pressure vessel or thin wall pressure vessels. So, we had to assume before we started deriving the solution, that we did in strength of material or solid mechanics. I will just come to that the very standard well known solution for thin wall pressure vessels that you obtained in strength of material course or in first year mechanics course. But here we have not made such assumption. Here we have not made any assumption whether the pressure vessel is thin or thick. We made some assumptions, but that assumptions are different assumptions. Linearity assumptions, stress strain relation is how the stress strain relation is, those assumptions, mainly in isotropic, those are the assumptions. But as far as the geometry of the problem is concerned, thickness of this in this case concerned, we have not made such assumption. But these assumptions were made in the solution, while obtaining the solution in strength of material or mechanics course. Now, suppose, so this is the expression for hoop stress, right? We obtained from the elasticity theory. This is sigma theta theta. In the previous slide, if you recall, this is the expression for hoop stress. Okay. Now, let us see if I have to find out. So, this is a very general expression. Very general expression means this expression is applicable for thick walled, and it should give me the result at the limiting case, the result for thin wall pressure vessel as well. For instance, you recall the problem, this problem. You have a pressure vessel, very thin pressure vessels which is subjected to some internal pressure, say P. Okay. And suppose the radius of this pressure vessel is R and thickness is T. So, and the hoop stress is say sigma hoop stress is this. So, we derived some relation between hoop stress R, T and P. Okay. Now, this is the expression for sigma theta theta. Now, suppose if the pressure, if this problem, if I consider this problem as a limiting case of this problem, then what happens? Then we have P2 is equal to 0, and then we also have T is equal to R2 minus R1, and we also have, since T is very small, it is thin wall vessel, then R1 and R2 is also very close to each other, and therefore, the average R0 is equal to R1 plus R2 divided by 2, which is R here. So, this is equal to R. Okay. So, if I in the limiting case, if I have to consider this case the limiting case, this we have to impose this condition on this expression. Okay. Now, let us substitute this, substitute this condition. Now, then sigma theta theta becomes what? Then sigma theta theta becomes minus, you see, if R1 is equal to what? R1 is equal to, in this case it will be R0 minus T by 2, and R2 will be R0 plus T by 2. Now, similarly, then R1 square, there will be a nonlinear term of T, R1 square and R2 square if we take, there will be nonlinear term of T. Since T is very small, we can remove this nonlinear term, and we will see that this will be almost R0 to the power 4. Okay. So, this term will be R0 to the power 4 in the limiting case when T is very small, and then sigma theta theta becomes R0 to the power 4, R0 to the power 4, and then P2 is equal to 0, this is minus P1. Suppose P1 is equal to say P. So, this is P, and then this becomes 1 by R0 square, and R2 minus this become R2 minus R1 into R2 plus R1, R2 minus R1 becomes T, and R2 plus R1 becomes 2 into R0. Okay. Then plus this term P2 is equal to 0. So, this become R0 square, this is P, and this becomes T into 2 R0. So, this becomes essentially, finally, it becomes P by 2, then we have R0 into T sigma theta theta. So, no, there will be no T2 term, because 2 will be this is the final expression R0 into T. So, you recall in strength of material or in your mechanics, first year mechanics, for thin wall pressure vessel you obtain the expression as this, and we just now saw this expression can be obtained from this expression as a special case. So, next what you can do is you can try one thing, you plot take a plot where you plot T here, thickness, which is R2 minus R0, R2 minus R1, and then you plot sigma theta theta here, and then see how the sigma theta theta varies with thickness, and then you will see that when thickness is very small, then this will give you the result from the, that is also you can show graphically results that you obtain from obtain in mechanics, first year mechanics or strength of material. So, this is the beauty of this formulation, that we do not have, this is more general, and with this as we apply this theory for say beam bending problem and also for torsion problem, then we will also see that some of the assumptions that that actually used while deriving the methodology in your mechanics course or strength of material course, and those assumptions we do not have, and therefore, we can get a solution which is more general, and that solution give you more insight into the actual into the behavior of this behavior of the different problems. Okay. So, now with this, so next is suppose, so we have a solution for this problem, we have a solution for this problem, just we have solved it. Now, next suppose we have a problem like this, where we have an infinite plate of infinite dimension, and then we have a small hole where you have some internal pressure. So, with this solution from this problem, we can obtain solution from this problem as well. You see, one extreme case we have seen that the thin wall pressure vessel can be considered as a special case of this problem. This also can be considered as a special case of this problem, and in order to use the solution of this problem, for this what we have to do is we have to use it that P2 is equal to 0, P2 is equal to 0, and R2 tends to infinity if this is infinite, isn't it? Now, we can get a solution from this problem as well. In that case, what will happen, that in that case R2 tends to infinite, and then P2 is equal to some value, say sigma, and P1 is equal to 0. So, if we have a problem like this, and then with the solution of this problem, we can obtain the solution of this and this as a special case of this problem by substituting corresponding this. So, what you can do is, you have to do one exercise. First exercise is you find out the solution of the first problem, this problem, and if you know any, if you are familiar with finite element method or any other numerical methods, you can find out the solution of, or if you are familiar with any software, say Abacus or ANSYS or any other software, you can model this, you can get the solution of the same problem, and then check the solution that you obtained from elasticity theory and the solution you obtained from numerical methods. Is that, are they same? Are they same under all circumstances, irrespective of the thickness, irrespective of the forces? Is there any discrepancy? If there is a discrepancy between the solution of elasticity theory and the solution of finite element method, that will give you an opportunity to understand what are the limitations of this solution, okay, because this solution is also based on certain assumption. Similarly, you can do all these exercise, not only this, throughout this course, whatever exercise problem, whatever example that we solve here, all the examples for which the elasticity solutions are obtained in this course, I suggest you to model this using finite element or any other numerical methods, using a software, or you can write your own code and find out the solution and compare the elasticity solution with the solution you get from those methods, and you try yourself, find out yourself what are the reason for the discrepancy, if there is any discrepancy at all. Okay. Now, before closing this, before we stop today, this we have seen how to get the solution of this problem, right? Now, suppose if we remove these forces, remove this stress, now we have just a stress, infinite plane, a plate with infinite dimension, and we have a hole at the center or anywhere, and then this plate is subjected to some uniaxial loading, uniaxial tension like this. See, whenever I say that infinite plate, it does not literally mean infinite, it means the dimension of the plate is very large as compared to the dimension of this hole. Okay. We will not find out the solution of this problem today, but the reason why I am stopping today's class with this problem is we will come to this problem once again when we talk about complex variable approach. But the reason we stop, next class onwards we will be applying the Array stress function using for beam problem, for torsion problem. This problem is important in many reasons. The reason is, suppose consider a problem like this. Just before stopping, take the same problem. Suppose this problem is an infinite plate with a circular hole. Suppose this hole is not circular hole. What happens if suppose this hole is an elliptical hole? Okay. So, for a circular hole we will solve, find out the solution, but suppose that hole is not circular, hole is elliptical hole, or suppose hole is elliptical, but then the minor axis is very small, or even further smaller, or consider a limiting case where this minor axis becomes so small that the hole becomes just a line, okay, and this line corresponds to crack, okay, or defects or material flaw. You see, this problem we will solve when we talk about complex variable approach. A general solution we will try to find out, and we will see when this circle becomes ellipse, then what happens to the solution, what happens to the stress field. We will also see if that minor axis of the ellipse continuously reduces, and then what happens, how this stress field continuously changes, and in the limiting case, on an extreme case, when that limit becomes a crack, when an ellipse becomes a line, the minor axis is so small, then what happens to the stress field, and that stress field will give us an opportunity to learn or to introduce rather a new subject called fracture mechanics. Okay. We will have a very brief introduction to fracture mechanics, linear elastic fracture mechanics, because we are talking about elasticity problem, and that is the reason I am stopping today with this example. Okay, then I will stop today. Next class we will apply these Array stress function for beams. See you in the next class. Thank you.